Okay, I have put the link, streaming link in the chat box. Let us continue. Okay, so in this question, so you have a set of functions. So identify which of them are vector valued and which of them are scalar valued. So for that, you first need to know what is the domain and what is the codomain. So for the first function, can you tell what is the domain?
R2.
R2. R2. And what is the codomain?
R1.
R. So if the codomain is R, is it scalar valued or vector valued?
Scalar.
Scalar valued, right? Yeah. And what is the domain in option 2?
R3.
R3. And what is the codomain?
R.
So is it scalar valued or vector valued?
Scalar value.
Scalar.
Yeah. What about option 3?
Domain is R3.
Domain is R3. And codomain is?
Codomain is R3.
So is it scalar valued or vector valued?
Vector value.
Yeah. What about this one? What is the domain and codomain?
R2.
Yeah. So this is vector value. Yeah. What about the last one? Domain and codomain?
R2R.
Yeah. So this is scalar value. Okay. Fine. So you have the basic understanding of what is scalar valued and vector valued functions. Okay. So remember, so whenever we are looking at graphs, so in 2D, whatever we have seen, it is like functions of one variables. Whenever you are looking at functions of one variable, what does it mean by graph of f for functions of one variable? For functions of one variable, what does it mean by graph of f?
The set of all the points x comma f of x.
Yeah, so for one variable functions, so graph is nothing but set of all x comma f of x. So you have the representation of the graph in 2D with x and y axis, right? Y axis usually representing the function values, f of x values. Similarly, suppose you are considering functions of two variables, then the graph of the functions is a set of all points x comma y comma f of x comma y. Okay, where x comma y is in the domain of f. Okay, so whatever you are getting here, so here usually whatever you are getting here, you call it curves, right? Similarly, whatever here you are getting in the graph, they are called usually surface. Okay, they are surface in space. Okay, so in the very beginning of calculus, we start with what is rate of change. Before that, of course, you see what are limits of a function, continuity and everything. Then the next thing you see is what is the rate of change, right? Rate of change with respect to a particular variable at a point. So in the case of one variable functions, rate of change of rate of change means, what does it mean? What does it mean, rate of change at a point? It is the derivative usually, right? Yeah?
Yes.
Same way,
Yes.
here rate of change, but here we are having more than one variable in the domain, right? For example, if the domain is Rn, you have n variables. Okay. So in that case, you have to talk about rate of change with respect to which variable you are talking. Okay. So that is defined in this way. By the way, do you remember how rate of change is defined for one variable functions?
Yes, ma'am.
Yeah. So so you have, for example, this blue curve is your graph, right? So what is the rate of change of this function? For example, at this particular point, how do you define? You define it in this way. You take this secant line and bring this as close as possible by making this h going to 0, right? And what is this slope of this tangent line? Is the limit of the slope of the secant line. And what is the slope of the secant line? F of x naught plus h minus f of x naught by h, right? So this is what we are doing in the case of one dimension. I'm just quickly recalling. I'm not explaining anything here. I'm just quickly recalling. By the way, this is one book which I find it easier for references. So if you want, you can also, this is easily downloadable, I guess. Maybe I'll show you the first page. This is yeah, calculus early transcendentals. Here start with one variables and you have everything up to multivariable functions. Okay, so this is one reference which I see, and it is having quite some examples also. You can have a look if you want. Okay, fine. Okay. Yeah. So here rate of change. Now we are talking with respect to one particular variable. Earlier this was just h. We don't have any ei. But now here you have ei. Why is that so? Because what is this ei? First of all, do you remember what are these eis for Rn?
Ordered, standard ordered basis.
Yeah. So you have the standard ordered basis where ei is all zeros with 1 in the ith coordinate. Your ith coordinate is 1 and all others are 0, right? So this is how your rate of change is defined. Okay, so just looking at this formula, you may find it very vague. Just let us look at this graph. So rate of change, just like rate of change is same as derivative in the case of one variable. In the case of multivariable, that coincides with partial derivatives. Okay, so what happens here? So imagine that this, you are having a surface here. Okay, what is a partial derivative of this surface? F of x comma y with respect to x at x naught comma y naught. At this particular point, x naught comma y naught, what is the partial derivative we are talking? So what is that we are doing? We are first of all considering the slice your y is equal to y naught. So for example, so let us say this is your y naught. Okay, so you are considering this slice y is equal to y naught. You are intersecting it with the surface. So what is the resulting? The resulting is this blue color curve. So this curve now looks like something in a two-dimensional plane, right? So the blue color curve is what we see in the two-dimensional case, right? So now what is the rate of change of this particular function? Now you are fixing this y naught, right? Only you are varying your x. Now only the x is varying and your y is fixed. Okay, so now you see that now your function dou f by dou x, f of x comma y. What is this? This partial derivative at x naught comma y naught is nothing but the derivative of the function f at f of x comma y naught, because now you are fixing y naught. So this is nothing but the derivative of the function with respect to x. Okay, and y naught is just a y, you are fixing it with the very constant y naught. Okay, similarly, when you are talking about partial derivative with respect to y at x naught comma y naught, then what are you doing? You are actually fixing the x value. So here your x value is x naught. Okay, so now you are considering the slice along x is equal to x naught, then you will have this particular curve. So what is your dou by dou y of f of x comma y? What is that you are fixing now? You are fixing x and varying y, right? So now it is d by dy of f of x naught comma y. So this is the derivative with respect to y, making this x as x naught and fixing this x variable. Okay, so you understand what is going on here? So in
Yes, ma'am.
general, you see that partial derivatives are again just derivatives by making one particular variable fixed and varying the other one, right? So for example, here this is the same definition will work here. So here you are making limit h goes to 0, f of x naught plus h comma y naught minus f of x naught comma y naught by h. So here y naught is fixed. So this is your partial derivative with respect to x, right? So here you are fixing your y and varying your x values. Okay. So you are the same limit is what we saw in the case of one variable also, right? So in the case of one variable, you had something like this, right? In the numerator, and the denominator was h, right? So the same definition you are getting here. Only thing, you are having another variable which is fixed here. That's all. Okay. Fine. So what is the general definition for partial derivatives? Limit h goes to 0, f of x tilde plus h ei. So how does this coincide with this? It is easy to see, right? So here the particular variable here is taken as x tilde. So here your x tilde is taken as x naught comma y naught. Okay. And here with respect to x means you are taking with respect to x means you are considering E1, which is 1 comma 0, right? So x tilde plus HE1 is nothing but x naught comma y naught plus h times of 1 comma 0. What is this equal to now? Right? This is your first term, right? So you see that the first term is x tilde plus HEI. In the case with respect to x, I'm talking about, and then minus f of x tilde by h. Okay, you see how this definition is coming? Yeah? Okay.
Yes, ma'am.
Yes, ma'am.
Okay. So this is the definition using limits, but you know how to do the derivative. You are already very familiar with derivative formulas. So straight away you can use the derivative formulas while computing partial derivative in most cases. In very special cases, you have to be careful because sometimes you see that you are either having some maybe piecewise functions, or you are having some problem with kind of the continuity or that particular point. So in those cases, you have to use this limit function. Okay, limit definition. Maybe we have some examples like that. At that time, I will tell you about it. But in general, you can use the general derivative formula for finding the partial derivative. Okay. So
Ma'am,
what is the rate? Yeah.
can we find the derivative of more than one variable?
With respect to more than one variable, for example, here you see that you have now 3 variables. You can find the derivative with respect to x or y or z. Anything is possible. Okay, so in the domain, how many different variables are there? So you can find the derivative with respect to all the different variables. Okay.
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 Ma'am,
Yeah.
but at the same time, can we say like x and y?
Sorry. What is your doubt?
Like we are doing only with one variable here. Can we do it for two variable at the same time?
No, 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 no.
Okay.
Okay.
That may come, ma'am, in the directional derivative.
Sorry.
Will it come in the directional derivative?
Even in the directional derivative, you are considering the rate of change with respect to one particular direction. Only one direction you are considering there also, not more than one direction. Okay. See, because we are considering slices, if you are considering more than 2 different slices, which slice will you consider? You are considering about the tangent in this slice. Suppose you are considering 2 different directions, then you have 2 different curves and 2 different tangent lines. So which slope of which tangent line will you consider as the derivative? Right? There will be ambiguity. So usually when you are talking about derivative, you are talking about derivative with respect to only one particular direction at a time. Okay?
Okay.
Yes, ma'am.
What is the rate of change of this function at 1, 2, minus 1 with respect to z? See, rate of change, as I told you, it is nothing but, you see, this is same as the partial derivative formula you see here, right? So rate of change of a multivariable function is nothing but the partial derivative. So when you are having such a question, don't think that it is something different. You are just talking about partial derivative with respect to which variable is given here.
Z.
Yeah. So what is fz?
X and Y will be constant.
Yeah, x and y are constant. So what is the partial derivative with respect to z?
6
6z minus 2y.
Yeah.
minus 2.
And you have to evaluate this at 1 comma 2 comma minus 1. So what is the answer? So you have to put z as minus 1 and y as 2. So what's the answer?
Minus 10.
Yeah. Okay, fine. Suppose f of x comma y comma z is given like this. Now this is a multivariable function defined on domain in R3. So is the first option correct? Is it scalar valued?
Yes, ma'am.
Yeah. The rate of change of f at this point with respect to x is 1. So first of all, what is fx? Tell me from this expression.
Y plus
Y
Z
plus Z minus
minus
3YZ.
Z minus 3yz.
Yeah. So now what is fx at 0 comma 1 comma 1?
Minus 1.
So 1 plus 1 minus 3, right? Which is minus 1. So here it is given as 1. So this option is incorrect. What about the third option? So f of the f partial derivative of f with respect to x at 2 comma 2 comma 2. So what is this value? Substitute here.
minus 8.
Yeah. So now they are asking, is it same as fz at 2 2 2? So what is fz?
Yes.
What is fz?
Y plus
Y
X
plus X.
Minus?
minus 3XY.
Yeah. So fz at 2 comma 2 comma 2 is going to be the same.
Yes, ma'am.
Yes,
So
ma'am.
you see that this is correct. Okay. So this is for option 2. This is for option 3. Okay. And the last one is rate of change with respect to y. So what is fy? X plus?
X plus
X
Z
plus Z
minus
minus
3
minus 3
XZ.
So what is fy at 1 comma 3 comma 5? 1 plus 5 minus 15, which is minus.
minus 9.
So this is fine, right?
Yes, ma'am.
Okay.
Yes, ma'am.
Okay, let f from R2 to R be defined as f of x comma y is equal to x cube plus 3xy. Identify the correct option with respect to partial derivatives of f. So what is fx?
3x square plus 3y.
And what is fy?
3X.
3x.
Yeah. So are they same?
No,
No,
ma'am.
ma'am.
So first option is incorrect. So now what is fx at fx fy? So what is the value at 0 comma 0? Fx value
0.
0,
and fy value
0.
0.
0. So they are coinciding. What about at 1 comma 1?
6,
6.
And
3.
3.
3. So they are not coinciding. What about at 1 comma 0?
3,
3,
3.
0. Okay, 3.
Okay. So now what about the fifth option? Dou f by dou x is equal to dou f by dou y plus 3. Y is
No,
missing,
ma'am.
right? So still incorrect. Okay, fine. A similar question here. Let f of x comma y is equal to xy by x squared plus y. Identify the correct options. So what is dou f by dou x?
3x square plus 3y.
3x square plus 3y. 3x square plus 3y. 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 First, what is dou f by dou x?
X square plus y plus
So you have to use which formula here?
u by v.
Yeah. So you have to use u by v formula. So if you are using u by v formula, so this is your u and this is your v. So you will have here v squared in the denominator and vu dash minus uv dash in the numerator. So use that formula and tell me what is dou f by dou x?
X square plus y
Yeah.
multiplied by whole multiplied by y minus xy multiplied by 2x
Yeah.
divided by x square plus y whole square.
Okay. So here we have kept y as constant. Remember that. Similarly, what is dou f by dou y? You have to keep x as constant now.
X square plus y x whole
Into x.
minus xy multiplied by 1 divided by denominator will be same.
This square is outside. Okay, fine. Now, what about dou f by dou x at 0, 0? So maybe if you want, you can simplify this. This is x squared y plus y squared minus 2x squared y by x squared plus y the whole square. So when you simplify, you get y squared minus x squared y by x squared plus y the whole square. So at 0, 0, what happens?
It becomes
0.
it is undefined.
It becomes 0 by 0 form, right?
Yes,
Undefined.
ma'am.
Yeah. Similarly, what this you will get a similar expression here as well. So here you are actually getting x cubed by x squared plus y the whole square. Here also you are getting 0 by 0 form. So you see that dou f by dou x are not defined at 0, 0. What about at 1, 1? What is the value of fx and fy at 1, 1? Substitute 1, 1 here.
0.
And what about fy?
1 by
1
4.
upon 4.
So the first option is correct. So this is incorrect. Here it is given as 0. What about at the point 1, 0? Anyway, this is becoming 0. What about this one? 1, right?
Yes, ma'am.
Okay. Fine. Okay. Let f from R2 to R be defined as f of x comma y. Now, this is a function and you are given that fx and fy are same at this particular point. Using this information, you have to find k. So what is fx from this?
2x plus 4y.
2x plus 4y.
Okay. And what is fy?
4x
4x
minus
minus
2y.
2y.
It is given that at 12 comma k they both coincide. So fx at 12 comma k is equal to
24 plus
4
4k.
plus 4k. And fy at 12 comma k is
48 minus 2k.
48 minus 2y. Okay.
so it is given that 24 plus 4k is same as 48 minus 2k. Solve this and tell me what is the value of k.
8, ma'am.
Value of k is
6.
4, ma'am.
4, right? Be
4.
careful.
Yeah.
Should be 4. Okay.
Yes,
So
ma'am.
you will get 6k is equal to 24. So k is equal to 4. All right. Okay.
Yes, ma'am.
So let f from R2 to R2 be given by f of x comma y is equal to p of x comma y, q of x comma y, where p and q are again multivariable functions. Now consider this matrix A given by this. So given that determinant of A is 0, find the value of xy. So what is first of all the matrix A? Let us compute. What is dou p by dou x?
6xy.
Just 6, right?
6, ma'am. Yeah.
Just
Just
6.
6.
Yeah, what is dou p by dou y?
2y.
2y.
And dou q by dou x?
6x.
And dou q by dou y?
2.
2.
2.
Yeah. And it is given that determinant of A is 0. What is determinant of A from this?
12
minus
minus 12
12
x
minus
12 xy.
So what is xy then?
1. 1.
Yeah. Okay. Fine. Consider a function f from R2 to R such that dou f by dou x is given as y times of cos xy. So which of the following functions are possible candidates of f? So consider this function. What is dou f by dou x for this function? So now,
y cos xy.
so you are having first sign of some function. Chain rule you should apply here. So
Yes,
you
ma'am.
have
Cos
cos
xy
Cos xy
and x.
multiplied by y.
Yeah.
into y.
So does it coincide? Yeah.
Yes,
Yes,
ma'am.
ma'am.
Yes,
So
ma'am.
option 1 is fine. What about option 2? What is dou f by dou x? So now you have to apply product rule and also chain rule together. So consider
Yes, ma'am.
this as your u and
First,
then v, then you have to apply. So u into v dash. So let us keep xy first. So xy and then v dash is sine of xy minus sine of xy.
minus
And then again this xy, when you apply chain rule, you will get an
Y.
y.
y square.
Have minus xy square plus what is the
Cos
remainder?
xy same.
Yeah, multiplied with
Y.
X,
Y.
y.
y. Okay. So this is not coinciding with this term. You have an additional term here. So this option is incorrect. What about option 3? So
No,
dou
ma'am.
f by dou x, the first term we have already computed the derivative, which is y cos xy. And the second term, the derivative is, what is the derivative of xy
Y.
with respect to x? Y.
I.
Yeah.
So here also this is not coinciding. You have an extra term. So this is incorrect. What about option 4?
It will be, ma'am, as cos y will be 0, right?
Yeah. So here you will see that the first function you see fx here, the first function we know already, it is y times of cos xy, and the second part it is a function of y alone.
It will be
So when you
constant.
find the derivative with respect to x, it is 0, right? So it is coinciding with the option. What about option 5? Yeah.
That phi is a linear function or what?
See, whatever, whether it is a linear function, so only one thing we should keep in mind is that this should is this maybe you can have something like non-constant, not a constant function. Okay, so this is not a constant function. Maybe this assumption is needed. So if it is not a constant function, then you know that the derivative will have not a constant and also not a linear function also, as you said. In the case of linear function also, if the coefficient is non-zero, you will have some numbers anyway. So anyway, not a constant assumption is sufficient. Linearity is not required. Not a constant is sufficient. So
So
sine,
this will also give the extra term, right?
yeah, so we will have an extra term. So you will have phi dash of x, right? So option 5, you will have fx is y cos xy plus phi dash of x. So you see that this is not coinciding. What about option 6?
It will coincide, right? As
Yeah.
phi y
Whatever
will
we
be 0.
take doesn't.
Yeah.
And
So the
second
second
term will
term
be
will
0.
become 0. Yeah. So this is coinciding. All right. Okay. Consider the function f from R2 to R defined as follows. F of x comma y is equal to square root of x squared plus y squared. Okay. So now this is whole part 1 by 2. So how do you find the derivative with respect to x? How do you find the derivative with respect to x?
1 by 2
1 by
multiplied by x square and then minus.
Here also you need to apply kind of chain rule along with the power rule. So first if you apply power rule, what is it you are getting? Nx power n minus 1, right?
Yes, ma'am.
Power
Yes,
rule.
ma'am.
So if you apply that,
X
what is
square
that you
plus
are
y square
getting?
to the power minus 1 by 2.
Yeah. So you will have 1 by 2 times of x squared plus 1 y squared whole power minus 1 by 2. So the square will come in the square root will come again. So now applying chain rule, what will you get? So you have
2x.
to differentiate the function here. So you are getting 2y or 2x.
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 So what is the answer? X by.
X upon under root x square plus y square.
Okay. And what about fy?
We just have to replace y in the
Y
numerator.
by root of x square plus y.
Okay. So are they defined at 0 comma 0?
No, ma'am.
No.
Okay. So you see that this is incorrect. They does not exist. What about at 1 comma 1?
Yes, ma'am.
It's 1 by root 2.
1 upon root 2.
1 upon root 2. Okay.
Yes, ma'am.
Fine. This option is also correct. Okay. So the next topic is directional derivative. So for directional derivative, so instead of considering directions which are along the axis. So for example, if it is along the x-axis or y-axis or z-axis, now we are considering any unit vector. Okay. So you don't have to consider any specific direction, but any arbitrary direction. Okay. So it can be any unit vector. For example, earlier we considered only the unit vector along x-axis and y-axis. Now you can consider along any unit vector. For example, maybe 1 by root 2 comma 1 by root 2. Okay. So something like this. So any unit vector direction you can consider. So the definition is just similar. So instead of h times of ui, now you have h times of this u. Okay. So what is that you had in the case of partial derivative? You had f of x tilde plus
E1.
hei minus f of x tilde. This is what you had. Now what is that you are having? You are having f of x tilde plus hu. That's all. So instead of ei, you are having u. That's all is the difference. Okay. Fine.
Yes, ma'am.
So remember, the directional derivative of a function along ei is nothing but is a partial derivative. If your u is ei, it will just become partial
Partial.
derivative along xi. Okay. Remember that.
Yes.
Okay. And what is your gradient vector or gradient function? So suppose you are having a function of several variables, then you find the partial derivatives with respect to each of these variables in the domain and put them as a vector. That will give you the gradient vector. Okay. So what is the domain of this gradient function? Set of all points where all the partial derivatives exist for that point. Okay. So for example, can you find the
Ma'am, can
gradient?
you repeat the definition again?
Okay.
Yes,
So
ma'am. Please repeat how to do it.
maybe if I do this example and go back to the definition, it will be easier, I guess. See,
Okay.
what is, suppose you are having this function, what is partial derivative with respect to x and what is partial derivative with respect to y?
With respect to x, it is cos xy.
Y sin XY.
Y
Cos
Y cos
xy.
xy.
and with respect to y,
X cos x. X
X
cos
cos
x.
XY.
okay, and what is fx at 0 0
0.
0.
0.
and fy at 0 0?
0.
0.
Okay, so you see that first of all, this is fx comma fy, which is y cos xy comma x cos xy, and del f at 0 comma 0 is 0 comma 0. Okay, so what is del of the gradient function is simply the partial derivative with respect to x and with respect to y written as a vector, written as a vector. Okay, so that is what I said. So you have to write the partial derivative with respect to each of this variable. Here you only have two variables, so you have written the partial derivative with respect to these variables. And here if you have n variables, you are writing it with respect to each of the variables. Got it?
Yes, ma'am.
Okay.
Yes.
So now tell me what is fx here?
2x.
2x.
And what is fy?
2y.
2Y.
What is fz?
2z.
2Z.
Okay. Now what is your gradient function? Gradient function is fx, fy, and fz. Now what is del f at 1 comma 2 comma minus 3? So what is fx at 1 comma 2 comma minus 3?
2
4 minus 6.
4 minus 6. Okay.
minus 6.
Ma'am, there was some other name also for this inverted triangle, right? Something with n. Like,
Nebula.
what? Nebula?
Usually we don't use that. We just say gradient f here.
Okay.
Okay. Fine.
Ma'am, what it shows the gradient vector?
Gradient vector is the partial derivatives of the function with respect to each of the variables in the domain, written in the vector form.
This is the solution part, ma'am, but what it shows in the geometrically?
No, it is not showing anything geometrically. It is just giving you the function as a derivative function. That's all. See, what is a derivative function?
Okay.
So
Gradient function.
Slope of a tangent. So
yes,
this.
see, when you talk about one variable, you are having only one direction. Now, gradient function is giving the derivative with respect to any direction in the domain. Okay, any axis direction. Okay, that's all. Geometrically, there is nothing much about gradient vector, but when you talk about directional derivative in terms of gradient vector, there is some significant thing about the gradient vector. But now you just see it as a function. Okay, geometrically, there is nothing much about gradient vector alone. Okay, fine. Okay, now consider this function. See, whenever you are having such functions, you are having piecewise functions, you have to be careful while you are doing the partial derivative. So you have to do the partial derivative for each piece separately. So here, what is a partial gradient function for this f of x comma y? Can you tell?
Ma'am, so f of x would be x square plus y square y minus x 2x upon x square plus y square the whole square. And similarly for y we can find.
Yeah. So whenever you are dealing with piecewise functions, you have to find the derivative separately for each of the pieces. Okay. So here one piece is when x comma y not equal to 0. So first, if x comma y not equal to 0 0, then what is your fx? What is your fx in this case?
X square plus y square multiplied by y.
Yeah.
And 2x multiplied by xy.
Okay. Fine. So when you simplify this, you will get correct. So I
Yes.
can further simplify it as okay. Now what is Fy when x comma y not equal to 0, 0?
And just replace the terms. X cube minus y square x.
So here you have x, xy into 2y by x squared plus y squared the whole square. So you will have x cube minus xy squared by x squared plus y squared the whole square. Okay. Now what happens at 0, 0?
We need to find by first
And
principle.
both are 0.
So you have to be careful here whenever you are having something like this. So straight away finding derivative is not advisable. You should better use the limiting formula. Okay. So what is the limiting formula when you use dou f by dou x at 0, 0? What is the formula here?
Limit as x tends to 0 f of x naught plus h.
So here your x naught is 0. So simply, yeah,
Yes.
this is fine. Now what is f of h comma 0? According to this first formula,
Ma'am, h comma 0, how did you get? Can you make sure?
so it is f of x tilde plus he1, right?
Yes, ma'am.
So f of x tilde here, this is your x tilde, correct?
Yes.
0,
It's
0,
0, 0, ma'am.
h times of, yeah,
Okay, ma'am.
right?
Yes, ma'am.
So now 0, 0 plus h times of 1, 0 is nothing but h comma 0, right?
Yes, ma'am.
Yes, ma'am.
Fine. So now what is f of h comma 0?
It's 0, ma'am.
Minus
X,
h
Y,
h square square.
You will have h by
Ma'am, we will have 0, no, ma'am,
yeah,
because
it is
y
Yes.
is 0.
Yes, ma'am.
0 by h, so which is 0. Okay. And what about dou f by dou x? Sorry, dou y at 0, 0 again?
It becomes 0 f of h comma 0. We will put in the above formula, right? Y
Yeah,
cube minus x square.
yeah. Okay. And what about this one? Limit h goes to 0. Can you tell the expression here? What should be the expression here?
0,
0 comma
h.
0 comma h minus 0 comma 0.
So which is again, what is f of 0 comma h again?
0, ma'am.
Yeah.
0.
Okay. So usually when you are having some piecewise functions, particularly when one piece is just 1 point, please use this definition. Don't just write it straightforwardly. Okay. Fine.
Yes. Yes, ma'am.
Piecewise functions, you have to be a little careful. Okay.
Excuse me, ma'am.
Yeah.
In such cases, you're saying that we have to use partial derivatives and then go ahead with it. Because
What's your question?
they have asked if the limit exists, right? Or how is it like? What is the question basically? What are they asking? Whether it's
So we are finding the
find the
gradient.
gradient vector. Okay.
Yeah.
Okay. Got it.
Okay. So in this case, the gradient vector also you have to write it del f at you are not asked about any particular point. You are writing it as a function itself. So this function also is a piecewise function. The gradient vector is also a piecewise function. So you have to write it as comma x cube minus xy squared by x squared plus y squared the whole squared. This is when this bracket is not required. This is when your xy is non-zero, and it is 0 comma 0 if x comma y is 0 0. So this is your gradient function. Okay.
Yes, ma'am.
Yes, ma'am.
Now using
So,
this,
ma'am, when
yeah.
real number is given
Mm.
directly as an answer,
Mm-hmm.
then we use this first principle
See,
or any other
it's not
thing.
depending on whether real number is given. See, here you are having a piecewise function. So for piecewise functions, for each of these pieces, you are finding the derivative separately. So now here you are having only one point here. It is not an interval also. It is just one particular point. So what is the function at that particular point? How do you find the rate of change only at one point? You need to know what is happening on both sides of the function, right? To know the rate of change.
Yes,
Yeah.
ma'am.
Yes, yes.
So that is why here we are going according to this limiting function, limit definition. We are not straight away looking at, okay, it is 0, so derivative for this function with respect to 0 is 0. We are not doing that because here we are not having any interval. It is just, it is not any region. Just one particular point is there. So that is why we are doing in this way. Okay, got it?
Okay, ma'am. Yes.
Okay, so directional derivative, we have seen the limit formula. So now we can find the directional derivative using the gradient function as well. So how are we using the gradient function to find the directional derivative? So the directional derivative, and at particular one point, it can be written as the gradient function at that point dot product with the unit vector. Very simple.
Unit vector of which vector means which?
The directional derivative with respect to which direction that particular unit derivative, unit vector.
Okay.
Okay, so we'll do some very simple examples. So you are having the function f of x comma y is equal to x plus y. Now what is the directional derivative in the unit? So unit vector is not any specific number, it is just given as u1 and u2. So how will you find using this formula now? First you need to find what is the gradient function. What is the gradient function?
Y comma x.
1 come.
1 comma 1, right?
Yes, ma'am.
So what is here? Your du of f is del f of u. So not del f of u. So del f here, no particular value is given. So del f dot del f at x comma y dot here u. So what is the answer? 1 comma 1 dot u1 comma u2. What is the answer?
U1 plus U2.
Okay.
Yes,
Now
If they are unit vector, we don't have to do with that norm, right?
here since it is already a unit vector, we are not dividing it by its norm. If it is
Okay.
not a unit vector, then we have to divide. So what is del f now? Yeah, what
Y plus
is
u.
X.
y plus z? Then
X plus z.
X.
X plus y.
yeah. And what is du of f? So y plus z dot u1 comma u2. So here you have to be careful. u1, u2, u3 you have to take. Okay. So what is the answer here? Okay. Fine.
Ma'am.
Yes, ma'am.
What about the third one?
Y cos x
Y
y.
cos XY.
X cos x.
X cos XY.
And what is the directional derivative? Straight away you can tell u1y
Cos XY. plus u2 x cos xy.
Yeah. Okay, fine. Okay. Now look at this question. If the directional derivative of f at the point 2 comma 3 in this direction is a root 2, where a is in R, then find the value of a. Okay. So first, what is the, so here you are having, this is your a and this is your v. So u is v by norm v, remember that. Okay. So what is del f first of all?
Y minus,
Y minus 4y. And
yes,
And
uh,
X minus 4.
this is with respect to ax
1
first you
1
have to
plus
write, right?
y.
1
Yeah.
plus y.
Y comma x
4.
minus 4y. Okay. So what is del f at this point A, which is 2 comma 3? 4 comma
4 comma minus
Minus 10.
minus 10. Okay. Now what is your u? 2 root 2 comma 2 root 2 whole divided by its norm. What is the norm of this vector?
4 under root 16.
4.
So how do you simplify this?
Root 2 by
1
2.
by
1
root
by
2
root 2
comma
comma
1
1
by
by
root
1 by root 2 by 1 by root.
Okay. So just one note here. Along which line does this point lie? So
y equal
both
to
of
x.
the coordinates are x comma x basically, right?
X equals to y.
So what is the unit
equal to
vector?
x.
What is the unit vector along x comma x?
1 by
1
root
comma
2.
1 by root
1 comma 1 by root 2 comma 1 by root.
Okay. So some simple way to see what is the unit vector. Anyway, you can use this method also. No problem with that. Just I'm telling. Okay. So what is now the directional derivative at this point along this direction u? What is the answer?
Minus 3 root 2.
So it is
minus 6 root
6
2.
by root 2. And it is given that it is a root 2. So it means what? So du f at 2 comma 3 is given as a root 2 and our answer is minus 6 by root 2. So what is a then?
Minus 3.
Minus 3.
Minus.
Okay, clear?
Yes, ma'am.
Yes.
Okay. Find the directional derivative of the function f from R to R such that f of x comma y is given in this and in the direction of 3 comma 4. So what is your gradient function first of all?
6x minus 2y.
6x minus 2y.
Yeah. And then?
Minus 2x.
Minus 2x.
Minus 2x.
Okay. So what is your unit vector?
3 by 5 comma 4 by 5.
So what is the directional derivative of f along u? What is the answer? What is the answer?
26x minus 6y
10x
upon
minus 6y by 5. So option 2.
But I missed this minus. Okay. So here is a minus sign. Okay. All these are incorrect. Okay. Any doubt?
Yes,
No,
ma'am.
ma'am.
How you have calculated this U?
What is U? As I told you already, U is nothing but unit vector. So V by norm V. Here norm of this vector is square root of 3 square plus 4 square, which is 5.
So, ma'am, basically we are finding the derivative in the direction 3, comma 4.
Yeah, exactly. Okay.
Yes.
Okay. Okay, look at this problem. Try to find the value of k by yourself. Everyone try to do this yourself. Sorry. So, what is that you will do first?
Find the gradient.
Yeah. What is the gradient function?
Minus 20 e raised to the power minus 2x.
Are you sure?
No, ma'am. E raised to power same रहेगा.
Yeah.
Minus x square plus y square minus 4z square.
Anything else missing?
Into x.
Yeah. And then?
And 20y e to the power of x.
How did that x come? Minus 20x.
Chain rule, right? When we are applying chain rule, what do you do? So you are having e power f of x, right? So when you are applying chain rule for this, first you do f dash of x and then write e power f of x. So what is f dash of x in this case? Minus 2x.
X. Okay, okay.
Okay.
Yes.
Okay. So here, what is with respect to z?
Minus 80j. It will be minus 18.
Yeah,
It will be
correct.
minus 80.
Correct, correct. Now you are considering at the point 2 comma minus 1 comma 0. So what is this? Evaluate and tell me. Minus 40 e per, what is e per?
Minus 3.
3.
Minus 3.
Yes, ma'am.
So x squared is 4, y squared is 1. So minus 3. Okay. And here minus 20 e per minus 3 and
0.
is 0. And what is your unit vector?
1
1 by
by
root 3.
Yeah. Now what is the rate of change at, so what is your rate of change? So let us call this point to be A tilde at A tilde along U. What is this? Right? And they have given the answer as k times of e power minus 3 by root 3. So let us do the dot product. What is that we are getting? Minus 40 plus 20 e power minus 3 by root 3. So which is, yeah?
Actually, in the delta F, the second coordinate will be positive 20 power minus 3.
Y is minus 1, right? Yeah?
Okay.
So now comparing LHS and RHS, what is your K?
Minus
Yeah. Is this fine for everyone? Yeah?
Yes, ma'am.
Yes, ma'am.
Okay. So again, a simple problem only. You are given a function. So if this is the directional derivative at this point along this unit vector, and V is another unit vector, you have to first find the matrix and then determinant of A. What is this A? First of all, can you find it quickly? So first, what is del F? What is del F?
2x minus 2y.
Yeah.
2y minus 2.
Okay. And they are already unit vectors, so you don't have to convert it into unit vectors. So what is duf at 1 comma 2? You have to multiply this with the unit vector 1 by root 2 comma minus 1 by root 2. So what is that? So first of all, what is del f at 1 comma 2?
It's minus 2 comma 2.
It is
minus 2 comma 2.
okay. So what is the answer? Minus
4
minus
by
2
root.
by 2 minus 2 by root 2.
So minus 4 by root 2, or you can write minus 2 root 2. Okay. So I guess this is just a computational problem. Shall I leave this as a homework? This is not
Yes, ma'am.
much.
Yes, ma'am.
So I'll
Yes, ma'am.
the homework. Okay. Fine. Okay. So limits of sequences of real numbers you already know. So for example, if you are having sequences like 1 by n, what is the limit of 1 by n? Is it a convergent sequence?
Yes, ma'am. 2 0.
Yes.
Yes.
What is the limit of 1 by n?
0.
0.
Yeah. So as n goes to infinity, this goes to 0. Is this familiar to you?
Ma'am, e exponential 1.
Yeah, it is just e, right? So this is e. This goes to 0, this goes to e. What about this one?
1.
1.
This is 1, right?
Can you explain, ma'am, how it goes to 1?
So this one, usually when you have like this, so you know this rule, right? Limit theta goes to 0, sine theta by theta. What is this value?
1.
1.
So using the similar concept, these are one variable things. So I guess I will do it quickly, assuming you know it. Can we rewrite it in this way?
Okay, ma'am.
Yes.
Yes, ma'am.
Fine. So what about this? Is it convergent or divergent?
Divergent, ma'am.
It's actually
Oscillating.
oscillating, right? So as n goes to infinity, this is oscillating. This goes to infinity. Divergent. This is also going to infinity. So these are all divergent sequences. So these are real sequences which you already know. The same concept we are going to use for limit of sequences in RP. Okay. So instead of just one sequence, you are going to have a set of sequences written as a vector like this. Okay. So now each of this coordinate is now representing a sequence. Okay. And this limit will exist if a and I goes to ai for each I. So each of the sequence should have a limit. Then only this entire sequence will have a limit. Okay. So for example, look at this one. So as n goes to infinity, does the first coordinate have a limit?
Yes.
0.
And what about this one?
Yes.
1.
So what is the limit of this sequence as n goes to infinity?
0, 1.
Yeah. Now what about this one as n goes to infinity? What happens to this?
This is
This
oscillating.
Divergent.
and this is 1. So does the sequence limit of the sequence exist?
No.
No.
So limit does not exist. So you know the short form, right?
Yes.
Does not exist. Okay. Fine. What about this one?
That is 1.
This is 1 or 0?
0.
0.
0, right? Okay. What about this one?
5 by e square.
You have to be 5 by e square, exactly. You can break down this into steps and see what is the limit of the first one and then second one. So what is limit of n goes to infinity ln 1 plus n? Ln is an increasing function. So what happens to ln 1 plus n as n goes to infinity?
Infinity.
0.
Infinity.
So 1 by ln 1 plus n will go to
1 by
0.
0. This whole term will go to 0. And here this term will go to 5. You know how.
Yes.
And what about the denominator?
e raised to
Infinity.
2.
1 plus 1 by n whole power n, that is that as n goes to infinity will go to e.
E.
So the square of that will go to
E square.
E
square.
square.
So this limit is 5 by e square. Okay.
Yes,
And
ma'am.
what about this one? You already know
E.
e. And what about this one?
0.
Does not exist.
0.
This does not exist. You have to be careful here. This does not exist. Okay.
Can you explain this one?
See, what about this one?
It's 1.
See, if we are trying to rewrite it in this way, does it work here? It does not work, right? Because here n goes to infinity, and here what happens? As n goes to infinity, this is actually going to 0, right?
0. Yes, ma'am.
Yeah. So seeing that in this way does not work here. Okay. Fine. So in general, if one of the limit does not exist, the overall limit does not exist. Okay.
Yes, ma'am.
Yes.
Right. So now you have these basic examples, you know, power rule for limit of functions, right? So this limit is ai power k. What about this one? Here for k greater or equal to 0, this applies. For k less than or equal less than 0 also will the same apply. This is just power rule, right? So k, if it is less than 0 also will it apply?
Yes.
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 So the limit should be just ai per k. What about this limit?
E power AI.
Yeah. What about this one?
Log
Log of AI.
What about remember here AI is positive is important, otherwise it is not defined. What about this one?
Sine A tilde.
See here we are not considering x tilde. We are considering only xi. So
AI.
AI.
Means
This
what
only
is
works when the left hand and the right hand limit are same, right?
Sorry?
This only works when the left hand limit and the right hand limit are same. That's why we are replacing it with A.
Yeah, here we are having this kind of so polynomial functions. So power rule we are first seeing, and then exponential function, logarithmic, and then trigonometric. These are continuous functions we know. That is why straight away we are writing them as the limit of just the functions value at that point. These are continuous functions which we already know.
Ma'am, that AI is there as we are only considering one element of x tilde and A tilde.
X, just one coordinate, yeah.
Okay.
And here what's the answer? See here AI is between minus pi by 2 and pi by 2. So it is not taking any pi by 2 value. So here it is tan of
AI.
AI. Okay. So some general limit rules. I guess these limit rules you already know. So these kind of rules, whatever you have seen for real functions, similar rule applies here as well. Okay. Composition and sandwich principle. So all this, whatever is there for real function, the similar rules apply for multivariable functions also. Okay, fine. So when in the next thing is actually very important, limit of a function at a point along a curve. Okay, what does that mean? So in the case of one variable, when do you say first of all a limit exists?
When LHL is equal to RHL.
What LHS?
LHL, left hand limit and right hand limit are same.
Yeah. So left hand limit and right hand limit first of all should exist and they should be equal, right? So here, for example, I will give you a simple function maybe. Maybe consider this function. So how does this function will look like?
Step function.
So let us say this is your 1 and this is 1, this is 2, let us say. So the graph for x less equal to 1, it is 1. And greater than 1, it is 2. So what is limit x goes to 1 f of x? Does it exist?
No, ma'am.
No, ma'am.
Why it does not exist? What
Because
about
it
the
is not
left hand
continuous.
limit? Left hand limit is
1.
and right hand limit is
2.
2. So you see they do not coincide and hence the limit does not exist. Let me give another example. So let us take f of x is equal to 1 by x So how does this function will look like? So here it is 0 up to this, and here it is something like this, right?
Yes, ma'am.
So, if it is like this, then what happens to the left hand limit and right hand limit? First of all, do they exist?
No, ma'am.
So you see in this case, the right hand limit at 0, does it exist?
It goes to infinity, right?
Yeah. So you see that limit x goes to 0 plus f of x does not exist at all. So this limit of this function at 0 does not exist. So these are the generally two scenarios in which the limit does not exist in case of one variable. So either the left hand limit and right hand limit does not coincide, or maybe one or both of the left and right hand limit does not exist. Okay. So similar concept is there for functions here also. Here, instead of just left and right hand limit, there are several ways to approach one point. Okay. So that several ways you call curves. So you can take any curve passing through that point, and what is the limit of that function through that curve? That is what we are seeing in this case. Okay.
But this is for one variable only.
No, I just first told you what is happening in one variable. Now I am talking about functions of several variables. Okay. So
Yes,
now you are considering a function of several variables. Now what happens to the limit of this function at a particular point? For that, so you can take any curve passing through that point in the domain. Okay. So the limit of that function along this curve is equal to L. Okay. If for every sequence an in C which converges to A, f of an converges to L. Okay. So instead of just left and right, now you have any curve C which passes through the point A. Okay. So we will look at examples that will make this more clear. Okay. So now consider this function. This is obviously a multivariable function. Now what is the limit of this function at 0, 0? Okay. So curves, usually what are the curves we consider? First, we usually start with x-axis and y-axis. Then we move with any straight lines, and then we move to parabolas. Okay. So usually these are the curves we start with. Okay. Okay. So what happens along x-axis? Along x-axis, what is the value of y?
0.
So you see x-axis passes through the point 0, 0, right? So what happens
Yes, ma'am.
along x-axis? So this function reduces to?
So we need to take any curve which pass through that point and
Exactly.
then find the limit.
Exactly.
So it will be x
Now what is limit
cube,
x going to 0?
x cube by x to the power 4.
X cube by x power 4. So what about this limit?
1 by x.
It's
And
infinite.
Go to 0.
does this exist?
No, ma'am.
No, ma'am.
Does not exist.
So if this does not exist, you can say that this limit does not exist.
Even if for one case it doesn't satisfy,
Yes.
then for the whole we
Yes.
can say.
Yes. Just like here, even if one side limit does not exist, we say that a whole limit does not exist. Same here. Okay.
So, ma'am, we are applying the same thing as partial derivative. We are just doing it for one at a time.
Yeah. Yeah. Okay. Fine.
So, ma'am, suppose it did exist for this, then we will check for how many curves and.
See, usually, this is the next theorem here. See, finding the limit is actually particularly for multivariable function, unless it is some specific polynomial or continuous function like this, which is given here. So it is very difficult to find the limit of multivariable functions in general. Okay. So usually whatever here we are having techniques only to say that the limit does not exist. What is the technique? So to show that limit does not exist, so either you should produce a curve for which the limit does not exist, or you should produce two different curves, so along which the limits are different. Okay. So this is what usually we are doing throughout these examples, unless for very familiar examples. Okay.
Only we are disproving that the limit does not exist.
Yes. Maybe for some very obvious examples where the limit exists is very easily seen. Otherwise, you are usually disproving that the limit does not exist.
Okay, ma'am.
Okay. Okay. So in this case, how do you see whether the limit exists or not? So usually I told you we start with the x and y axis. So let us start with the x axis. What happens along x axis?
It's 1, ma'am. Like x square, x square.
So y is 0 here. So if y is 0, what happens to the function? So what is the limit?
1.
Okay. Now along y-axis, your x value is
0.
so limit y goes to 0. Here, what is the function you have?
Minus
y square by
minus
y.
y square y square minus 1.
Yeah.
Minus.
So are they equal?
No,
No.
ma'am.
They are not equal. So if they are not equal, what can you say?
Limit does not exist.
Okay, fine.
Ma'am, suppose it is there for means it exists for x axis and y axis and both are same, then we will take another curve.
Yes, yes.
And how would we decide that which curve to take?
Yeah, we will do few more examples and then you will know. Okay.
Okay.
Okay. So now again we'll start with something like you said. Along x-axis, y is 0. So now what is your limit as x goes to 0? What is the
0.
function?
0.
Right. Now along y-axis, your x is 0. So limit y goes to 0. What is the function?
It will be 0.
So in both the cases, now it is coinciding. So the next thing we will move on to maybe y is equal to x. What happens along y is equal to x?
X square upon
X
2x square.
What is the answer?
1/2.
So this and this, are they coinciding?
No.
No.
No, ma'am.
Yeah,
Limit
they
does
are.
not
So the limit?
Does not exist.
Okay. Now what happens?
So ma'am, all the curves should pass through 0, 0 only.
See, usually either the limit x comma y go to 0, 0. Sometimes 1, 1 or some other different points are also asked. I guess you can see such questions in PYQ sessions. Okay. I will tell the TS to particularly solve problems where it is not 0, 0. Okay. Since
Yes.
I did not cover it here, okay, here are few examples, but these are like functions, different type of limits. But anyway, I tell the TS to cover such limits also. So along x-axis and y-axis, just like the previous one, obviously, what is the limit along x-axis and y-axis?
0.
Limit is 0. Okay. So next along
Y equal to
Y
x.
equal x.
y equal to x, or sometimes you can generally take y equal to mx also. So if you take y equal to mx, you are considering all straight lines passing through origin. So what happens in this case?
Mx cube upon
M square x square.
So what is the answer here?
1/1 plus x square.
So here, when you take this m square commonly, so what is that you will get?
And it should be x cube on
Sorry,
the
x square common.
M square by 1 plus m
1
to
plus
the
m
power
raised to
4 x
4
square.
x square.
So what is the answer here? It is
M square.
m
M
squared.
square.
So if it is m squared, did I miss something here? Y is equal to
Ma'am, it's m square.
Numerator, ma'am, x cube.
cube, right? Yeah, it's x cube. So here you have x. Now what is the limit?
0.
0. Now still you don't have any different things. Then what to do? Which curve to take? Now you move to parabolas. Y equal to x squared, or here they have taken x equal to y squared. I guess that is the easier option here. X equal to y squared. So what is the limit?
Ma'am, in numerator it will be y to the power
Y
4.
power 4, right?
Y squared is your x, right?
Okay.
Same.
Yeah. Same.
1 by
2.
and it is non-zero. So does the limit exist?
No.
Okay. So usually this is the way you keep on moving. So sometimes it is very obvious that the limit exists. Otherwise, you have to see along which curves the limits are different or the limit does not exist. Okay. So these are the usual curves you take. Usually we don't go beyond parabolas. Okay, usually that is the kind of problems we choose. We don't go beyond parabolas. Okay.
Ma'am, what are some obvious examples
Where the limit exists,
Yes, ma'am.
maybe something like linear functions or something like polynomial functions.
Where the 0 by 0 or infinity form doesn't appear.
Yeah.
Okay.
Okay. So limit of vector valued functions, it is just like limit of the sequences here. So here instead of the sequences of one variables, now you have sequences. Sorry, instead of sequences, now you are having functions here. So a similar concept like we did earlier. So now instead of one function here, you have f1, f2, f3. So you have to find the limit of each of this function. If the limit of each of the function exists, then only this limit exists. That's all. Okay. So what is the limit of f1 first of all? f1 is just a polynomial function, right? So what is the limit of this function at 1, 2?
2.
Be careful.
10.
It
10,
is?
ma'am.
Yeah. And what about limit of f2 of x comma y?
Ma'am, why didn't
E
we
square.
like previous thing? Why didn't we pass it through any of the curves?
Here, why didn't we proceed? You are asking?
So, ma'am, in this question, we passed it through x-axis and y-axis. So, in the previous question that we were doing, why didn't we do that? Ma'am, previous means the current one which we are doing, the vector valued one. Why did we directly apply the
As we told you,
values?
for polynomial functions and for exponential functions, where the limit is straightforwardly, you can see that it exists. You don't have to check whether the limit exists. So these are very straightforward functions, as I told you. Okay.
We can directly plug in the values.
Yeah, yeah. And even for this is like a quotient function. But this quotient function for 1, 2, there is no ambiguity in the denominator. But whereas in the previous cases 0, 0, there is some problem with the denominator. So that's why we are checking all this. But here there is no problem with the denominator. So straight away you can apply the quotient rule here for limits. So what is the answer?
0.
What is the answer?
0.
0, ma'am.
0. So what is the limit?
10, comma e square, comma 0.
Okay. Similarly, what about this function? This we already know. Sin theta by
1.
theta as theta goes to 0 is
1.
1. And what about this one? I guess we just did this problem. Or we didn't do. Okay.
Ma'am,
What
does not
about,
exist.
why it does not exist?
Ma'am, because the denominator, it will go to 0.
You should
We
not
have to check
argue.
again.
Yeah, you should not argue it in that way. You should see along which curves they are different. Okay.
Yes, ma'am.
So this maybe I'll give it as a homework. So this does not exist. I'll tell you that.
So the whole limit will not exist now.
Evident only the denominator itself.
Just by looking at the denominator, you cannot conclude. You have to give this kind of argument to say that the limit does not exist. So you have to use either of this to conclude the limit does not exist. Okay.
Yes, ma'am.
Yeah. So the whole limit does not exist. Okay. So what is the continuity definition for one variable? What are the 3 points you should have for continuity of a function?
Left hand
And if the
limited by
limit exists at a point, and it should be equal, the function at that point is
The
equal to.
limit is equal to right hand limit is equal to function value at that point.
Yeah, these are the points, right? So if all the 3 are satisfied, you know that the function is continuous at A. So the similar argument is here as well. So if the limit of the function exists at a point and the function value, if these two first of all exist and the limiting value is same, then we say that the function is continuous at the point. The same definition holds for multivariable functions as well. Okay?
yes, ma'am.
Okay. So continuity means the limit at A can be obtained by evaluating the function at A, right? Just like we see in the one variable case. Okay. So now you have a function here. We are going to check whether this function is continuous at the point 0, 0 or not. Okay. So check if G is continuous at 0, 0. So how do we do that? First of all, at 0, 0 is the function defined.
Yes, ma'am.
Okay, so what is the next thing we need to check then?
Left hand
limit.
Sorry.
Yeah, this is the next thing we need to find, whether this limit exists or not. So how do we find the limit of this function?
Ma'am, we take the same case
X-axis
like
and
along x-axis, along y-axis.
X-axis, y-axis curves.
Okay, so that is when the limit does not exist. Now here, what about the numerator and the denominator? When x comma y is non-zero,
It will be some. It will give some value.
yeah. See, one thing you notice is that is g of x comma y vanishing for any non-zero values?
No.
For x comma y not equal to 0, g of x comma y is always non-zero, right?
Yes.
This is always non-zero. So it means, is it possible that these non-zero values are converging to 0 as this value is function is going to 0?
You have to take limit of both of them to check at 0. L, L hospital rule, something.
Yeah. So here you see that limit so what is the argument to say that limit does not exist at 0 comma 0?
We have to prove that it does not pass through any of the curve. Means the limit does not exist.
Ma'am, we need to check the limit for both numerator, right? Both shouldn't be equal to 0.
See, maybe we have to use some curves and check whether it is existing at 0 or not. So can you check whether, so one thing we can say that for non-zero points, limit x comma y going to any a1 comma a2, g of x comma y, it is simply going to be g of a1 comma a2. For non-zero points, can we say that g is continuous? Yeah?
Yes.
So this is something you should note. So g is continuous for all x comma y non-zero. This is something to note. At 0 comma 0, what is happening? So you have to choose appropriate. So this is the exact curve we just saw here, I guess, right?
Yes.
Yeah. So at 0 comma 0, how does the limit not exist? This is the homework I gave you. So work it out along which curve the limits are different or the limit does not exist. That is what you need to find out. Okay. I guess maybe if you take along x is equal to x-axis, then y is 0. So what is that you get? Along x-axis?
X cubed by x4. So we'll get 1 by x.
Yeah. Along x-axis, you will get x cubed by x power 4. So here itself you see that. So limit x goes to 0. The limit does not exist, right? So you see the limit does not exist. All right?
How ma'am?
Yes, ma'am.
Okay.
Ma'am, 1 by x converges to.
As x goes to 0, 1 by x, what is the
Oh,
limit?
no, it does not.
Okay. Okay, which of the following functions f and g from R2 to R are continuous at the origin? So the first one is a piecewise, first and second both are piecewise function. But the first function you see, there is some problem with the denominator. So when x and y are non-zero, it is fine. Otherwise, you need to be careful. So what about this function? Is this function continuous at the origin or not? Yeah? What is your guess?
No.
Okay, how do we prove that it is not continuous?
But first we have to prove if it is continuous at every other point other than 0.
Mm-hmm.
And
So,
then we have to check for 0 comma 0.
okay, so see, this is just a note. You don't have to check this every time. This is just a note here. Okay, you don't have to check this every time. This is just a note. Okay, you don't have to check this every time for checking at 0 comma 0. So at 0 comma 0, whether the limit exists or not, how do we calculate?
We take one of the curves now.
Yeah, so which curve shall we try? Along x-axis, let us start. So along x-axis, y is becoming 0. Right? So what shall we do? How do we proceed?
You can use y is equal to x.
Ma'am, we can see that it is 0.
It is 0
Means
when?
it does not exist.
It is 0 when?
Along x-axis.
Along x-axis, it is 0. Why?
Ma'am, not 0. It does not exist.
Okay, so tell me along which curve it exists or it does not exist. How do we prove it?
We can take y equal to x, then it will be x cubed by 3x cubed, 1 by 3. It wouldn't be equal to the second one.
Which is the second one?
If we take y equal to x, it will be 1 by 3, right? And second limit is given as 0.
Okay, so let us take along y is equal to x. Okay, so if you are taking along y is equal to x, so you are saying you will get x cube by 3x cube, limit x goes to 0, which is 1 by 3. Okay, so suppose you are getting along y is equal to 2x, then what will you get? What will you get? What is the limit?
1 by 6.
1 by 6.
Are they equal?
No, ma'am.
No, ma'am.
So the limit does not exist, right?
We can also show this it doesn't equal to 0, that 1 by 3. Then also it is
Yeah,
not
yeah.
continuous.
Anyway, see what are the simplest way that you are doing. You can choose any curves. So these two I felt easier, so I am doing it. So you can choose
Yes.
any curves and prove it. Okay. So this does not exist. So you see, this is not continuous at origin.
Ma'am, why did you not take x-axis? Because we can directly see along the x-axis it is not, it does not exist.
See, along x-axis, what happens to y value?
It becomes 0.
If it is becoming 0, so when y is becoming, denominator is becoming 0.
Yeah. So it does not exist.
Yeah, it does not exist. Okay. So either you can do that or you can do this. Anyway, you can say. So this is not continuous or at origin with any of the arguments. What about the second one? Now what is this?
Polynomial function and continuous.
Polynomial function. So very cleanly you can apply the limit, right? So in this case, is the function continuous at origin or not? When you apply 0, 0, what happens?
0.
Yeah. So is it continuous at origin?
Yes, ma'am.
Yes.
Yes, ma'am.
So this is continuous at origin. Okay. Okay. So in whole, what are the things we have seen? First one, whether a given multivariable function is scalar value or vector value. Okay. And then we have seen what is rate of change, and rate of change is same as partial derivatives. And partial derivatives, after this we saw directional derivatives. These are nothing but directional derivatives along xi. And then what are directional derivatives along unit vectors we have seen. And that we can find using the gradient function. Right? And then what else we have seen? We have seen limits of multivariable functions. And then we also saw limits of sequences in Rn. Right? And then we saw continuity of multivariable functions. So these are the main topics of week 9, more or less like 1, 2, 3, 4, 5, 6 topics maximum. Okay. So is it clear for you all the topics we have seen in week 9? Any doubts?
Ma'am, in the last question, can you it is asking for continuity at origin, and
Yeah.
we have shown that the other two limits are not equal. So
Mhm.
how does it say it is not continuous at origin?
The third point fails. For the continuity, you need all these 3 points. First, this exists and this limit exists and this limit equal to f of a. This limit does not even exist. That is what we have shown. Okay? The limit does not exist. Only if the limit exists and it is equal to f of 0, comma 0, then only the function is continuous at 0, comma 0, right?
Yes.
Ma'am, I still don't get.
Okay. So these are the 3 points you need to verify for continuity.
Yes, ma'am.
Okay. Okay, any questions?
Ma'am, can you with the